Professor Belfrost's computer science class is back!
Okay, so welcome back to my class, and today I'll bring you the second part of our lesson on digital logic. Previously, we have reviewed about digital logic to with number system, right? The second part of number system. So I want you to pay more attention here because this is very important. So let's review a little about the last lesson. So in the last lesson, we learned about two's complement. Okay, so two's complement is expressed by doing invert or complement to all of the integer bits and adding one. And this is very useful because actually uh, we just use the mathematical principle of the two's complement of an integer, which is its additive inverse. Boolean algebra can be useful to describe functions of digital circuitry and develop simplified implementation of the functions. And we make use of variables and operations. A variable may take the value of 1 or 0, and an operation may take one of these, and or not, NAND, nor, and XOR. Okay, so well, there are many basic postulates and other identities that are useful in solving Boolean operation. And the fundamental building block of all digital logic circuit is gate. Okay, interconnection of gates will make the functions. Okay, so gate is just an electric circuit that produces an output signal that is a simple Boolean operation on its input signals. And each gate is shown uh, with one or two inputs, and the only gate with one input is not gate, and this is also the only gate with one output. So actually we have two kind of circuits. We have combinational and sequential circuit. We have discussed about combination circuit, which is an interconnected set of gates whose output at any time is a function only of the input of that time. And as with a single gate, the appearance of the input is followed almost immediately by the appearance of the output with only gate delays. And any Boolean function can be written as sum or pos form, okay? Sum of product or product of sum. There are three methods mainly to simplify Boolean expression. One of them we have discussed before, which is algebraic simplification. Then two others is Karnaugh maps and Quinn-McCluskey tables that we'll review in okay. So yeah, Karnaugh map. Karnaugh map is a very useful map which is actually an array of 2 to the power of n squares representing all possible combinations of values of n binary variables. Okay, actually you can have any n values with these, okay, but mostly we only do until I think 4 variables, because if we are using more variables and more variables, then it will be very complicated and it is very difficult to simplify using Karnaugh maps. So we have I've prepared figure for you, but it is on the next slide. I will explain it first, okay? So figure A on the next slide will show you the map of four squares for a function of the variable. And we need to very careful about how to list the combination, as the order is a little different. We have the order is 0, 0, 0, 1, 1, 1, and 1, 0. Okay, for three variables, then we need an arrangement of 8 squares. You need to remember it, 2 cube, okay? And for 4 variables, then we need 2 raised to the power of 4, which is 16 squares, okay? Which is indicated in the arrangement of figure C. So here it is, A, B, C. Please pay attention. So the map can be used to represent any Boolean function in the following way, which is its square corresponds to a unit product in the sum of products form, with a 1 value corresponding to the variable and a 0 value corresponding to the nut of that variable. Okay, so let's start from figure A. So each such product in the function and one is placed in a corresponding square. And for the example, then this is very clear that we want to express the function a b naught plus a naught b. Okay, a dot b naught plus a naught dot b. Okay, so given a truth table of a Boolean function, it's very easy to construct a map, kernel map. So for its combination of values of variables that produce a result or output of one, which is in the table below, is indicated with the letter F. Okay, then you need to fill in the corresponding square of the map with one. So here's the figure that shows the result of the previous figure. B, the truth table is below. Okay, so it's very easy, right? I want you to learn by yourself. So for example, we have equation F equals A naught B plus B naught C naught. We must first expand it into the full form of equation, which is F equals A naught B C naught plus A naught B C plus A B C naught, and then convert this to a map. Then you ask why we need to do this. The answer is relatively simple. We have three variables, so actually every term that we use in the function need to have three variables too. How to change from this to the three variables form, I have explained it in the previous lesson, so I recommend you to watch the previous video first before going through this explanation. Okay, so the labeling used in figure D also shown in the previous slides. Okay, so it emphasizes the relationship between variables and the rows and columns of the map. And here, the two rows embraced by symbol of A are those in which the variable A has the value 1, and the row not embraced by the symbol A are those in which A is 0. Similarly for B, C, and also D. And once the map of a function is created, we can now write a simple algebraic expression wherein by noting the arrangement of the ones on the map. And the principle is as follows. Any two squares that are adjacent differ in only one of the variables. Okay, this is the reason. I've noted this before. Okay, I want to tell you why we have 0, 0, 0, 1, 1, 1, and 1, 0. Why not 0, 0, 0, 1, 1, 0, and 1, 1? This is the reason actually. Okay, because any two squares that are adjacent differ in only one of the variables. This makes us to have a very easy things to do when we simplify it using kernel maps. So if two adjacent squares both have an entry of 1, then the such corresponding product terms differ in only one variable. And in such a case, then the two terms can be merged by eliminating that variable. Okay, for example, see the figure A below, okay? A below, okay? A not BD, okay? You can see, right? So the two adjacent squares correspond to the two terms, which is you can zoom it, okay? That is A not B, C not D, and A not B, C, D. So after we combine them together, it will result in A not B, D. Simple. And this process can be extended in several ways. First, the concept of adjacency can be extended to include wrapping around the edge of the map. It is shown in figure B and C, I think. Okay, so you see they are not actually grouped in the middle part of. They are not to side by side, but it is like bottom and top or left and right. But you can do this. Okay, it's actually wrapping up. Okay, and the second thing is that we can group not just two squares, but more than it. Yeah, we can do the grouping with 2 to the n adjacent squares. For example, 2, 4, 8, etc. Okay, the next three examples, which is D, E, F, show you how to group it. Okay, we have 4, 4, 4. Okay, and how about G, H, I? Okay, we have more grouping. We have 8, 8, 8. Also, some of them not adjacent to each other. Some of them are leftmost, rightmost, topmost, and bottommost. That's the thing that you need to pay attention to. Okay. So here's the summary. Okay. So first, among the marked squares, squares with a 1, then find those that belong to a unique largest block of 1, 2, 4, or 8 of and circle those blocks. Second is that select additional blocks of marked squares that are as large as possible and as few in number as possible, but include every marked square at least once. The result may not be unique in some cases. Okay. The third is to continue to draw loops around single marked squares or pairs of adjacent marked square or group of 4, 8, and so on in such a way that every marked square belongs to at least one loop. Then use as few of those blocks possible to include all marked squares. And here's the figure based on the table we used before, so it's a simplification process. Yeah? This is the figure at the middle, okay, of the slide. Okay, you see, we group it, okay, 1 1 1 1, okay, vertical, horizontal. Okay, we have figure A and B, right? Okay, see, you need to try to explain it by yourself. Okay, finally, before going from the map to a simplified Boolean expression, any group of ones that is completely overlapped by other groups can be eliminated, which is shown in figure B. Okay, you see we have a redundancy here. Okay, actually it's fine, but this is not the most simplified Boolean expression. So because we see that there's something that has been covered by the other group, they don't need to do this again. So the 1 1 horizontal part is not needed. Okay? One additional feature of kernel maps needed to be mentioned here. Okay? In some cases, certain combinations of values of variables never occur, and therefore the corresponding output will never occur. Okay? And these are the conditions referred to as don't care conditions. Okay? For each such condition, the letter D, or sometimes some literature will use X, okay, cross symbol, okay, which is entered into the corresponding square of the map. And the D or the cross one, okay, can be treated as either 1 or 0, which one is the convenient one to make the simplest expressions possible. And here's another example. We would like to develop the Boolean expression for a circuit that adds 1 to a packed decimal digit. Okay, so for packed decimal digit is represented by a 4-bit code. Okay, which is, for example, 0 is 0000, 8 is 1000, 9 1001, and we don't use 10102111. Okay, we only want to express 0 to 9. Okay, so here's the table showing the truth table for producing a 4-bit result that is one more than a 4-bit BCD input, and the addition is modulo 10. Okay, and noting that 6 of the input codes produce don't care result because they are not valid BCD inputs. Maybe you need to take screenshots. So here's the figure that shows the resulting kernel maps from each of the output variables, and D are used to achieve the best, and the D squares are used to achieve the best possible groupings. Okay, for example, you see, it's convenient in A to cover the D, two on the right or two on the rightmost and one on the leftmost, the bottom part. Okay, but for the B picture, you see how they cover it. Okay, we cover it DD, the middle part, left part. Okay, and then the rightmost is we have one D with us. Also, we have D at the bottom. Okay, and etc. etc. Maybe you need to do some, um, yeah, sketch and try to understand by yourself. So for more than 4 variables, the kernel map method will become very cumbersome. And with 5 variables, 2 maps are needed, and with one map considered to be on top of the other 3 dimensions to achieve adjacency. And 6 variables is even much mad. Okay, it requires the use of 4 tables in 4 dimensions. Can you do it? I think no. Okay, I cannot do that. Okay. So here's the alternative that I can give you, which is doing the tabular technique, which is called the Queen McCluskey method. And the method is suitable for programming on a computer to give an automatic tool for producing minimized Boolean expressions. And the method is best explained by means of an example that I can give you. Consider we have following expressions that needed to be simplified. ABCD plus ABC not D plus ABC not D not plus AB not D plus A not BCD plus A not BCD CD not plus A not BC not D plus A not B not C not D. I think I've missed something here. Okay, maybe the fourth term is A not B not C not D or A not A B not C. We'll see it later. Okay, don't worry. Let us assume that this expression was derived from a truth table and like to produce a minimal expression suitable for implementation with the gates. Then the first step is to construct a table in which each row corresponds to one of the product terms of the expression. And the terms are grouped according to the number of complementary variables. That is, we start with the term with no complements. If it exists, then all terms with one complement, and so on, so on. So here the table showing you the list for our example expression, where horizontal lines used to indicate the grouping. Okay, so for clarity, each term is represented by a 1 for each uncomplemented variable and a 0 for each complemented variable. Thus, we group terms according to the number of ones they contain. And the index column is simply the decimal equivalent and is useful in what follows. The next step is to find all pairs of terms that differ in only one variable, that is, all pairs of terms that are the same except that one variable is 0 in one of the terms and 1 in the term other. And because of the way in which we have grouped term, that we can do this by starting with the first group and comparing each term of the first group with every term of the second group. And compare each term of the second group with all the terms of the third group and so on. And whenever a match is found, and please place a check next to each term. Combine the pair by eliminating the variable that differs in the two terms and add them to a new list. Thus, for example, for the terms A not BC D not and A not BCD, then they are combined produced to ABC. This is the result. Okay, and this process continues until the entire origin table has been examined, and the result for the previous examples is here. We have BC not D, A not BD, ABD, and BCD. Okay, pay attention to the check one. So the new table is organized into groups as indicated in the same fashion as the first table. The second table is then processed in the same manner as the first, and that is a term that differs only one variable check and a new term produced for a third table. And in this example, the third table that's produced contains only one term, BD. Okay, and in general, the process will proceed through successive tables until a table with no matches was produced. And in this case, this has involved three tables. This example. Okay, and you can see in the illustration below. Okay, so each row of the matrix corresponds to one of terms that have not been eliminated in any of the tables you so far. Each column corresponds to one of the terms in the original expression, and cross or X is placed at the intersection of a row and a column that is the row element is compatible with the column element. And that is the variable present in the row element have the same value as the variables present in the column element. Okay, next circle is X or cross is alone in a column and then place a square around its cross in any row in which there is circle cross. If every column now has either square or a circle square, then a circle cross, I mean not circle square, then we are done. And those row elements whose cross have been marked constitute the minimum expression. Thus, for our previous example, then the final expression is ABC naught plus ACD plus A naught BC plus A naught C naught D. You maybe have to review this error, you have to rewatch to understand what I mean here. And cases in which some columns have neither a circle nor a square, the additional processing is required. Essentially, we keep adding row elements until all columns are covered. Okay, so here's the summary how this method works. So first phase of the operation is reasonably straightforward. This elements are needed variable in product terms. Okay, thus the expression, for example, ABC plus ABC naught is equivalent to AB. Then after the elimination, we are left with an expression that is clearly equivalent to the original expressions. But maybe there are many redundant terms, okay? The matrix layout assures that each term in the original expression is covered and does so in a way that minimizes the number of terms in the final expression. Another consideration and implementation of Boolean function considers the type of gates used. It is sometimes desirable to implement Boolean functions solely with NAND gates or solely with NOR gates. And although this may not be the minimum gate implementation, has the advantage of regularity, which can simplify the manufacturing process. Consider here, we have equation b dot sum of a naught and c naught. Because the complement of value is just the original value, okay, you can see. And applying the Morgan's theory, we obtain this. Then we have three NAND form, which is very simple to be implemented in manufacture, and it is illustrated as below. So sometimes we need it actually not the simplest form, but it is useful in manufacture because it simplifies the gates we need, the variant gates that we need. Okay. Next, let's discuss about multiplexer. Okay, so what is multiplexer? It connects multiple inputs to a single output. Okay, at any time, one of the inputs is selected to be passed to the output, and general block diagram representation is shown in the figure below. Please see the left one. And this represents a 4 to 1 multiplexer. Okay, there are 4 input lines D0, D1, D2, and D3, and one of these lines is selected to provide the output signal F. Okay, the right one. Okay, and to select one of the four possible units, then a 2-bit selection button S2, S1 is needed. An example for 2-1 multiplexer is defined by the truth table in the table on the right side. Okay, this is a simplified form of a truth table. Instead of showing a possible combination of input variables, then it shows the output as data from line D0, D1, D2, and D3. And figure below show how to implement this using AND or NOT gates. Okay, so S1 is connected to the AND gates in such a way that for any combination of these two, then three of the AND gates will output 0, and the 4 AND gate will output the value of the selected line, which is 0, 0, and 1, and thus three of the inputs to the OR gate are always 0, and the output of the OR gate will encode the value of the selected input gate. And using the regular organization, it's very easy to construct a bigger size for like 8 to 1, 16 to 1, and so on. Okay, please pay attention why we have this picture. Okay, you maybe want to find the reason by yourself. Okay, so multiplexers are used in digital circuitry to control signal and data routing. For example, it's used in PC program counter. So the value to be loaded into program counter may come from ones for different sources, for example, a binary counter, the instruction register, or the output of the LU. Then these various inputs could be connected to the input lines of a multiplexer with the PC connected to the output line. And because the select line determines which value is loaded into the program counter, and because the program counter contains multiple bits, then multiple multiplexer will be used at one per, and each one for each bit. Okay. So here's the figure that show you how this works for 16-bit addresses. Okay. You have three multiplexer, three 4 to 1 multiplexers here. Okay. PC0, PC1. Oh no, not 3, 16 actually. Okay. You see the ellipsis from PC0 to PC15. Okay. Next, we are done with multiplexer. This is just a very short review. We'll not do a very review about this. So now also talk a little about decoder. So what's the decoder? A decoder is a combination circuit with a number of output lines, only one of which is asserted at any time depending on the pattern of input lines. And in general, decoder has n inputs and 2 raised to the power of n outputs. It's not 2n, 2 raised to the power of n outputs. Okay. So here's the figure showing a decoder with 3 inputs and 8 outputs. Decoders find many uses in digital computers, for example, for address decoding. Suppose we wish to construct a 1 kilobyte memory using 4 256 times 8-bit RAM chips, and we want to single unified address space, which can be broken down as follows. Okay, here's the address range and which chip to be allocated, and each chip require 8 address lines, and these are supplied by the lower order 8 bits of the addresses, and the high order 2 bits of the 10-bit addresses are used to select one of the 4 RAM chips. And for this purpose, a 2 to 4 decoder is used here, whose output enables one of the 4 chips as shown in the figure below. Please pay attention how we allocate this. Okay, so with an additional input line, the decoder can be used as a demultiplexer, and the demultiplexer performs the inverse function of a multiplexer. It connects a single input to one of several outputs, and this is shown in the figure on the bottom. Okay. So as before, n inputs are decoded to produce a single one of outputs, and all the output lines are ANDed with a data input line, and thus the n input accesses the address to select a particular output line, and the value on the data input line 0, 1 is routed to that output line. And the configuration in the figure below can be filled in another way. Let's change the label on the new line from data input to enable. This allows for the control of the timing of the decoder. And the decoded output appears only when the encoded input is present and the enable line has a value of 1. I'll talk about the ROM, on the memo a little. Okay, we'll learn more about this later. Okay, so combination circuits are often referred to as memoryless circuits. Okay, because why? The output depends only on the current input, and no history of prior inputs is retained. But there's one sort of memory that is implemented with combination circuits, namely read-only memory, not read-only, read-only memory, ROM. Okay, let's recall that a ROM, okay, though maybe you haven't learned this, but you need to know a little about ROM. What is a ROM? ROM is a memory unit that performs only the read operation, the read operation actually, not read, okay, read from. Okay, this is implies that the binary information stored in a ROM is permanent and was created during the fabrication process. Thus, a given input to the ROM, which is address lines, always produces the same output, data lines. Okay, and because the outputs are a function on the of the present inputs, then the ROM is in fact a combination circuit. A ROM can be implemented either using a decoder or a set of objects. For example, consider the table below. Okay, this can be viewed as a truth table with 4 inputs and 4 outputs. And for each of the 16 possible input values, the corresponding set of values of the outputs is shown. It can also be viewed as the defined contents of 16 4-bit ROM consisting of 16 words of 4 bits each, and the 4 inputs specify an address, and the 4 outputs specify the contents of the location specified by the address. Figure below shows how this memory could be implemented using a 4 to 16 decoder and 4 OR gates. As with the PLA, the irregular organization is used, and the connections are made to reflect the desired result. Okay, so far we have seen how the connecting gates can be used to implement such functions as the routing of signals, decoding, and ROM. And one essential area not yet addressed is that of arithmetic. So in this brief overview, we will content ourselves with looking at the addition function. Okay, so binary addition differs from Boolean algebra in that the result includes a carry term. Okay, actually we have carry too, right? When we are doing mathematical algebra, okay, a very basic algebra, we have carry, we have a borrow. It's the same here. Okay, binary addition have a carry term. Okay? If we had only do 0 0, it's 0 0 1 1 1 0 1, but we do addition 1 and 1, it will result in 0 with a carry of 1. Okay, so we wish to add two n-bit numbers. This can be done by putting together a set of adders so that the carry from one adder is provided as the input to the next. See the table below. Okay, we have the sum column and the carry column. The carry will be provided as the input to the next. Okay, so here the 4-bit adder depicted. So for a multiple bit adder to work, each of the single bit adders must have two inputs, including a carry from the next lower order adder, and a revised truth table appears in the table below. Okay, so two outputs can be expressed. Okay, we have sum. Okay, the sum one, you see the one or the sum column, and for a carry is a ones that light up for the C out column. Okay. So figure below shows how to implement it using AND or and NOT gates. Please pay attention. And thus, we have the necessary logic to implement a multiple bit adder as shown in the figure below. It is from the left part 2 actually. Okay. And note that because the output from each adder depends on the carry from the previous adder, that there is an increasing delay from the least significant to the most significant bit, and each single bit adder experiences a certain amount of gate delay, and this delay accumulates. And for larger adders, then the accumulated delay can be very high, which is not what we expected. Okay. And if the carry values could be determined without having to ripple through all the previous stages, then each single bit adder could function independently and delay would not accumulate. This can be achieved with an approach known as carry look ahead. Okay, so for example, we would like to come up with an expression that specifies the carry input to any stage of the adder without reference to previous carry value. We have C0 is as shown. Okay, A0 B0, C1 is A1 B1 plus A1 A0 B0 plus B1 A0 B0, and using the same process that we can obtain the C2. And this process can be repeated for arbitrarily long adders, and its carry term can be expressed in SOP form as a function only of the original inputs with no dependence on the carries, and only two levels of gate delay occur regardless of the length of the adders. For long numbers, this approach becomes excessively complicated, and evaluating the expression for the most significant bit of n bit adder requires an OR gate with the inputs and n gates with from 2 to the inputs. And accordingly, full carry look ahead is typically done only 4 to 8 bits at a time. The figure before shows how a 32-bit adder can be constructed out of four 8-bit adders, and in this case the carry must ripple through the four 8-bit adders, but this will be substantially quicker than a ripple through 32-bit adders. Okay, so we are done. We have no assignment today, and here's a little quote for you. So Anthony D'Angelo once said, "Become a student of change, and it's the only thing that will remain constant." Okay, prepare yourself with everyday change, and that's how you keep alive. Thank you for watching. Give a thumbs up, subscribe, comment, and share this video. And check our new website. Okay, https://sciencewithxyz.unaus.com. Keep watching, be thoughtful. I'll be back every Monday. Thank you and goodbye. See you.